Okay, hello viewers of mine. We are talking about graphing, and here is our learning target. I can read, interpret, and create a position versus time graph. So, I would like you to think back to when we had first been talking about velocity. We know that velocity is displacement over time, or you can go ahead and calculate it if you have two particular points of a position and time. We can say d2 minus d1 over t2 minus t1. And you might say, you know what? That seems very familiar. It seems very familiar. It sounds just like, what is it? The equation for slope, you might say? Why, yes. Yes, it does. We even would want to draw out if we had displacement on the y-axis or position. We kind of use position and displacement interchangeably. We probably shouldn't, but we do. Position on the y-axis and time on the x-axis. Okay, so when we're doing this slope, we're saying the change in position divided by the change in time. Lovely, lovely, lovely. So velocity is the displacement over or divided by the time interval. We already know that, and we say, hey, that's the same idea as if we had a position time graph, we take the slope of the graph, and that gives us the velocity. Yeah! So if we take a moment to look at position versus time graphs, make sure we have a good grasp of them. Let's see. If we draw out a lovely position time graph, I'm not using any specific numbers here other than the initials as like T0 and D0 as it's just zero values. Because I don't want us to focus too much on numerical values just yet. I just want you to see a basic change in what's going on. So line 1, we started at position 0, and then we moved along up until position 1. Okay, now how that means we're moving because we moved along the y-axis of a position time graph. Now, how far did we move and stuff like that, that we're not getting into the numbers, but we do realize that we moved, and we moved in the positive direction. And then line 2, time passed, but there was no change on the y-axis, so we're not really going anywhere. So maybe in line 1, you had gone out for a walk, and then line 2, you're stopping for a rest. Maybe you're checking your cell phone. Maybe you're talking with someone. Who knows? Line 2, the position hasn't changed though, so we're still at position D1. And then line 3, we are returning. We have our position is still going to be positive up until it hits 0, but we do have a negative change in position. So we ran or walked or whatever it is back to our original starting position. So that's why we're going to have a negative displacement. We have a negative displacement there. And we know what we just talked about in terms of slopes. We're going to have this line here is positive slope, which means positive velocity, because it's the positive slope of a position time graph. This has 0 slope, so that means 0 velocity. And then this guy has negative slope, so that means negative velocity. Good stuff. Hopefully that makes sense not only in the mathematical sense, but in the physically. I don't know. So before we get too far, because we are going to be dealing with a lot of graph stuff, I want you to think about what we can do with the graph. Graphs are much more than just pretty pictures. They give us a lot of information, and more importantly, they help us relate the different concepts together. That's stuff we had talked about earlier in the year. So there are 3 basic operations that we can do to a graph. The first one is something you've been doing for probably, I don't know, maybe 10 years. Just reading it as is. You look at the graph, you say, oh, I have a position time graph. At this time, this is my position. At this time, I have some other position. I can also look at my change in position, as in like subtract one position value from the other. So I can find my displacement, but I'm just reading as is. Pretty much since you first started doing graphs, that's what you've been doing. The next idea is you take the slope. That's something you haven't done for 10 years, but probably maybe 4 or 5 years at least. Taking the slope, you're doing the rise over the run, but you are introducing an entirely new concept. If you take the slope of a position time graph, you're getting velocity. Velocity is definitely related to position and definitely related to time, but it is its own concept. And this applies not only with position time graphs, but all sorts of other ones. It's the rate of change between these variables on the horizontal and the vertical axis. And then finally, the third operation, which you may not have actually done on a graph before, but you've done this outside of graphs all the time, you find the area under the curve. Now, most of the areas that we're going to be dealing with are triangles and rectangles. So if you think about the area of a rectangle, that is going to be base times height, or you can also say length times width. For a triangle, that's going to be 1/2 base times height, or 1/2 length times width. You might also possibly deal with a trapezoid. Okay, remember the good old days of trapezoids. You say, oh man, how in the world do you figure out the area of that? Well, you could say technically the 1/2 base 1 plus base 2, where this is base 1, this is base 2, times height, where this is height. Or, you know what would be so much easier is if you just said, you know what, chop that up, and I see, oh, I have a rectangle and I have a triangle. And that would probably be so much easier for you to be dealing with it. Most people are more comfortable with it that way. So let's continue on though. What information do I want? Anytime you see a graph, anytime you see a graph, you got to ask yourself these 3 questions. First of all, what type of graph do I have? And I do not mean, oh, it's a line graph, it's a bar graph, it's a pie chart. No. What type of graph do I have? We'll see that on the next slide. The next question, what is asked for? You got to read the question carefully. Read the whatever problem you're working on, read that carefully. And then the third guy is choosing your operations. We just went through the different operations that we can use. Okay, so how do I know what type of graph I have? Well, you look at the title. In this case, I have acceleration versus force. You can also, most graphs should have titles, but sometimes we're a little bit sloppy and scrubbish and we don't see any. So we can look at the axes. The axes should be labeled properly. You see acceleration on the y and force on the x, or acceleration on the vertical and force on the horizontal. And then finally, you can also look at the units on the axes, meters per second squared, and then newtons. So those are all different ways of making sure you know what type of graph you have. Because if you are not paying attention to that, and I've been doing this for decades, and if I'm not paying attention, I can definitely mess things up. If you are not actively saying, what type of graph do I have, then everything else is going to mess up. Okay, so for example, what do we have here? This is a position time graph. I know because, hello, it says position time. Also, the axes are labeled. So I've got some stuff going on my position time graph, and I want you to think about what is going on here for this diagonal line, this first line right here. Okay, we'll deal with a bunch of these. The first line right there, we are seeing a change on the y-axis. We're going in the positive direction. We're going away from our starting point in the positive direction. So we have positive motion. And we also have a positive slope, so that means a positive velocity. Now, how about for line 2? We don't have any change on the y-axis, so there's no displacement. That means there's no movement. You can also look at that and see that the velocity is 0 because the slope is 0. Now, if we look at line number 3, we're back to having a positive slope, a non-zero positive slope. Notice the slope for line 3, this guy here, is different from this guy. I mean, obviously, we can go ahead and calculate numbers, but we see The line 3 is going to be steeper slope. So that means a larger change in velocity for, larger change in position for a particular time interval. So we're going to have a larger velocity. Okay, so the motion and velocity are positive, but this line 3 has a larger velocity than line 1. And then finally, line 4, we're having a diagonal one again. So we are having some type of slope, but notice the slope is negative because it's like we're going downhill instead of uphill. So the slope is negative. We have a negative displacement because we'd be saying final, which is 0, minus initial, which is 40 meters. So we'd have negative 40 meters as our displacement, and that means we're going to have a negative velocity, because velocity is displacement divided by time. Time is always going to be positive. It's a scalar. Okay. All right. So we have the same graph as before. Notice, what happened to the title? How will we know what type of graph it is? Position versus time. Got to make sure we're thinking about that very carefully. What is the speed during the first 20 seconds? Well, if I have a position versus time graph, how am I going to get speed from there? Or velocity? It's in this respect, I'm not going to be very picky. So we know velocity is displacement divided by the time. So during the first 20 seconds, okay, so we're just taking the slope. We have a position time graph. I'm looking for the speed or velocity. The way I get that is by taking the slope. So the slope from 0 seconds to 20 seconds, the rise is 10 meters. 10 meters. The run is 20 seconds. So go ahead and do the calculation, and you get 0.5 meters per second. Oh, there it is. Okay, number 2, how far is the object from the start after 60 seconds? So starting at 0 and ending at 60 seconds. Once again, we say, what type of graph is this? You say, oh, we already did that. Yes, do it again though. It's a position time graph. Position time graph. And what am I looking for? I'm looking to see how far. How far means displacement. If I have a position time graph and I want to find displacement or my change in position, all I have to do is read it as is. In fact, I'm just subtracting one position from another. So 40 meters minus 0 meters is going to be 40 meters. Woohoo! Number 3, what is the speed during the last 40 seconds? Okay, so during the last 40 seconds, that's going to be this guy right here. And what is the speed? Well, we're saying speed or velocity as before. That's the displacement divided by time. Now, I did ask for speed, so I'm going to say speed is distance divided by time. And I'll explain why I chose that one in just a moment. So the distance for the last 40 seconds is going to be, well, 40 meters. 40 meters divided by 40 seconds. And what do I end up with? That's going to be 1 meter per second. So the reason I wanted speed instead of velocity is because I wanted you to just focus on the number crunching. If it were velocity, it would be negative 1 meter per second, which might throw some people off. Okay, so it's 1 meter per second. Oh, I kind of wrote over there. Oh well. And when was the object traveling the fastest? Okay, I have a position time graph, and I'm being asked about speed or velocity. So that means I need to think in terms of the slope. When was the slope the largest? That's when we're traveling the fastest. The slope was largest from 40 seconds to 60 seconds, as was pointed out on the previous slide. Good, good, good. Okay, a word of caution. One thing doesn't necessarily mean another. So there are different ways of describing aspects of a graph. We can say the slope of a position time graph is constant, or increasing, or decreasing. you cannot be constant and increasing at the same time. You can't be constant and decreasing at the same time. What you're just doing is you're describing a change or potential change in what the object is doing. So how the object is moving, right? The object is moving at a constant velocity, or the object is moving at a increasing velocity, and so on. As opposed to this list over here, you can't be 0 and positive at the same time. That's describing what the object is doing. Okay, so what the object is doing, as opposed to a change in what the object is doing. You say, okay, what I don't get it. What's the difference there? Think of this. You can have an object moving with a constant velocity. That velocity could be 0. That velocity could be positive. That velocity could be negative. The point is the velocity is constant, and the velocity is one of these values here. You could also instead have a velocity that is increasing. An increasing velocity could be positive, could be negative. It could be 0 for a moment. Okay, likewise for decreasing. A decreasing velocity could be negative, could be positive, and just for a moment could be 0. Okay, so it's important that we take one descriptor from each column while we are trying to express ourselves. But what I definitely want to emphasize is constant and 0 do not mean the same thing. As I just was saying, you can have a constant velocity that is positive, or 0, or negative. Constant and 0 do not mean the same thing. Increasing and positive do not mean the same thing. Decreasing and negative do not mean the same thing. To help emphasize that, I have some position time graphs. Well, let's say if I have a constant position that is positive. I could have a constant position that is negative, and I could have a constant position that is 0. Okay, and I tried to draw those lines the best I could. Okay, how about for an increasing position? So let's say I started at the 0 spot. Oop, go away. I start at the 0 spot, and I am increasing my displacement, my how far I am from some reference point, right? I could also have a negative increase in my position. I'm just going in the opposite direction. I'm getting farther and farther away from my reference point. I'm just moving in the negative direction. And then finally, this is if I'm not moving away at all from my reference point. So I have 0 displacement from my reference point. Okay, and then finally, I can also do this for negatives. Okay, so, or I'm sorry, for decrease, I messed it up. There, what's going on here? I can do this for decreasing is what I meant to say. So I'll do this for a positive position where I am decreasing my displacement from, or my distance from some reference point, which is the 0. I can do that for a negative decreasing of my distance from a reference point, and just like before, I can keep a nice 0 from my reference point too. Now you say, Fair, what do you mean? If the displacement is 0, are you really increasing or decreasing? No, not really. It's when we're talking about 0 displacement, we're not really going to be increasing or decreasing our displacement. That is, unless we're changing directions. But we'll get into more exciting stuff when we're talking about velocity. Whoo!